Today we discuss the simple group and the class equation of a group. First of all, the definition of a simple group. A group G which is non-trivial is said to be simple if G and E are the only normal subgroups of G, where E is the identity element of G. Okay, that means a group G which have only two normal subgroups G and E is one trivial and another is G itself. Then the group G is said to be simple group. The theorem states that let G be a group and H be a subgroup of G of index n such that order of G does not divide n factorial. Then G is not simple. Example, suppose order of G equal to 15 and G has a subgroup of order 5. Then G is to H, that means index of H equal to 3 and order of G is equal to 15 does not divide 3 factorial. That means G is not a simple group. Okay. Now we prove this theorem. Let S equal to AH, set of all left cosets of H in G. Then there exists a homomorphism psi G to AS where AS is the group of all permutations on S. Defined by psi g equal to tau g. Tau g belongs to AS is defined by tau g AH equal to GA of H, such that car psi is a subset of H. We shall show that car psi is not equal to E. If possible, let car psi equal to E, then psi G2 AG G2AS is monomorphism. Hence, G is isomorphic to the subgroup image psi of AG. Now, image psi, order of image psi divides order of AG by Lagrange's theorem, because the order of subgroup divides the order of group, and this implies order of G, because image psi and G are isomorphic, so their order must be same. So image psi replaced by G, and order of G is divides n factorial. A contradiction. So car psi is not equal to E. Thus, G has a non-trivial normal subgroup, and namely car psi, the non-trivial normal subgroup which is car psi, and so G is not a simple group. Okay. Here, this is a statement of the Callis theorem, psi G2AS, where AS is a subgroup of all permutations on S defined by this way. This is the theorem or statement of the Callis theorem, and we use Callis theorem, we get the theorem G be a group and H be a subgroup of G of index n, order of G does not divide n factorial, then G is not a simple group. So, is the group is simple or not, then we can use this theorem, and we give another result which is too much important, is that let G be a group of order 2m, where m is an odd integer. Then G has a normal subgroup of order m. What is the result? G is a group of order 2m, where m is an odd integer. That means, suppose order of G equal to 6, order of G equal to 26, order of G equal to 14. They are 2 into odd integer. All those groups has a normal subgroup of order m. In either words, G is not a simple group because G has a normal subgroup other than G and E. So, to test the simplicity of a group, we can use this result. Now, we prove the statement. By Cauchy's theorem, G is isomorphic to H of AG, where AG is a group of all permutation on G. Then the homomorphism psi G to AG is defined by psi G equal to tau G, and tau G is belonging to AG, which is defined by tau G A equal to G. Since G is of order, G is of even order, then there exists an element G belonging to G such that G square equal to E. Let A belongs to G, then tau G of A equal to G, and tau G GA equal to GGA equal to G square A equal to A. So, tau G is a product of M transposition since M is odd, then tau G is an odd permutation. since tau g equal to psi of g, which is belongs to image psi equal to h, then H contains an odd permutation. Now define a mapping F from H into the multiple group -1 1 by f of sigma equal to 1 if sigma is an even permutation, and f of sigma equal to -1 if sigma is an odd permutation. Then we can verify that F is an epimorphism. F is an epimorphism. Now by first isomorphism theorem, G quotient car F is isomorphic to image F. G quotient car F is isomorphic to image F. Hence, order of G quotient car F equal to order of the multiple group -1 and 1. That means order of G divided by order of car F, which is equal to 2, and order of car F equal to 2 into m divided by 2 equal to m. So this implies that car F is a group of order m, which is also a normal, is a subgroup of order m, and which is also normal subgroup. So we can conclude, if order of G equal to 2m, where m is an odd integer, then G has a normal subgroup of order m. In either words, we can say that G is not simple. So using this statement, we get lot of group which is not simple, such as the group of order 6, 10, 14, 26, 58, they are all 22 also, the group which is not simple, because all are equal to 2 into some odd integer. Now I move to the section which is a class equation. Let G be a group and which is finite, of course. Then order of G equal to order of Zg plus summation A is belongs to A minus Zg, G is to Ca. In our previous lecture, we proved this statement. Now, here we just use the equation actually, where A is a subset of G consisting of exactly one element from each conjugacy class. A minus Zg may be empty. This is a class equation. Okay, order of G equal to order of Zg plus summation A belongs to A minus Zg, G is to Ca. Or also proved G is to Ca, G is to Ca means order of CLA. G is to Ca means order of CLA, where CLA is a conjugacy class containing an element A. Okay, conjugacy class containing A. Okay. Now we move to the exercise. Let G be a group of order 12 and A belongs to G. If A has 3 conjugate in G, prove that G is not simple. Solution is, since G is to Ca equal to CLA equal to 3, that means index of Ca equal to 3. Index of C equal to 3. And also we can see that order of G, which is does not divide 3 factorial, that means G is not simple. G is not a simple. Now we give an exercise, prove that a subgroup H of a group G is normal subgroup if and only if H is the union of conjugacy classes of G. Solution is, let H be a normal subgroup of G. We shall show that A is equal to union of CLA where A belongs to H. Okay. So first of all, let H be a normal subgroup of G, and we shall prove that H is equal to union of CLA, A belongs to H. Let H belongs to capital H. Since H is normal in G, for all G belongs to G, this implies G H G inverse belongs to H. This is test of normality. This implies H belongs to CLH, which is subset of union CLA, A belongs to H. So H is a subset of, union CLA, A belongs to H. Conversely, X belongs to CLA, union CLA, A belongs to H, and this is implies X belongs to CLA for some A belongs to H, and this is implies X equal to C inverse for some C belongs to H, because CLA is a conjugacy class of A. So this, since H is normal subgroup and A belongs to H, so X belongs to also H, because C inverse is belongs to H. That means H belongs to H, and this implies union CLA is a subset of H. So in the first time H is a subset of this, and second time this union CLA subset of H. So both implies H equal to union CLA where A belongs to H. So one part is done. If H is a normal subgroup, then H is the union of conjugacy classes of H. Now we prove that if this condition holds, then we shall show that H is a normal subgroup. So suppose this is holds. So this implies H belongs to union A belongs to H CLA, and this is implies H belongs to CLA for some A belongs to H, and this is implies H equal to G inverse for some G belongs to G. This is implies G inverse G1 inverse equal to G1 G inverse G1 inverse. This is implies G1 A G1 whole inverse, which is belongs to CLA. Okay, that is G1 inverse is belongs to CLA for some A belongs to H. This is a subset of union CLA for some A belongs to H, where A belongs to H, which is equal to H. So G1 inverse is belongs to H, and that means H is a normal subgroup in G. Again, there is another problem. Let G be a group, H be a subgroup of G, and A belongs to G. Prove that N A H A inverse is equal to A N H A inverse. Okay. So let X belongs to N A H A inverse. This is a normalizer of A H A inverse. So that means this is implies A inverse X A H A inverse XA, which is equal to H. And this is implies A inverse XA